Okay, now we're going to move on and talk about new things in chapter 12, finish chapter 12 up. We're still talking about light and how it behaves, but so far we've been talking about how light behaves when it hits a reflective surface. But what about when light hits a non-reflective surface? Okay, so we have a couple options. What happens when light hits an opaque surface, like a wall? Well, when this happens, some of the light is reflected back, according to the law of reflection, but most of it is actually absorbed. By the opaque medium. Now, light can also hit transparent or even semi-transparent mediums. So think of something like glass or water. What happens then? Well, transparent objects allow light to pass through them, and some is also still reflected back. So some is reflected, again, according to that same law of reflection, but some passes through. So think of something like your windshield. I mean, obviously your windshield allows light to pass through it. Water, we can see through water. It allows light to pass through. We know that some is reflected because have you ever had the experience where you're looking through a glass, through a window pane, and you can see your own reflection? Well, that's the part that's being reflected. But then you can also look through a window pane and see outside. That's the part that's passing through. But an interesting thing happens when light travels through a transparent object. It bends a little. And this bending is called refraction. Okay, so look at the picture on page 400. Go ahead and turn there with me. I'll give you a few minutes, and I'm going to turn to it myself. So the picture on page 400. This shows what happens when we have an incoming beam of light, and that's reflected by the red line. Let me move this over here. We have this incoming beam of light reflected, represented by this red line, coming through air and encountering glass. Well, just as we've already learned, some of this incoming light is going to be reflected, and that's what this green arrow is showing. That's the reflected portion, and it's reflected according to the law of reflection. So theta 1 is going to equal theta 3. We're very used to this by now. But some of it will go through the glass and be refracted. And again, when it's refracted, the angle, it's bent a little bit, so this angle changes. So theta 1 will not be equal to theta 2 because as the incoming light comes in to the different medium, it bends a little bit. Okay, so that helps to show us what refraction actually is. Okay, so when light hits a transparent object, some of it is reflected, and then as it passes through, some of it is refracted. Okay, reflected and refracted. Okay, so why does this refraction happen? So we have to go back to some things we've already learned. Remember, light travels at different speeds depending on the medium it's traveling through. We've learned this already, but it was a few modules ago. So in air, we learned that light travels at 3.0 times 10 to the 8th meters per second, okay? But in a denser medium, like glass, let's just say, it travels much slower. Okay? But now the tricky thing happens that the frequency of the light must remain constant at that point of where it moves from the air into the glass. If the frequency doesn't remain the same, the item that we're looking at, its color would change, and we know that doesn't happen. So the only way to maintain that frequency is to bend it as it enters the second medium. So again, turn to your book and look at page 401, the picture there. I'll move my book here. Okay, we have some light traveling through the air and then hitting glass. It travels through the glass, but it is refracted. So what I want you to look at here is the crests are what these perpendicular lines are trying to show. Okay, and those crests determine the wavelength and the frequency. Well, at this point right here, where we're traveling from the air to the glass, we have to maintain that same frequency or wavelength. And the only way to do that is to bend this green part of the light wave that's in the glass. Okay? What else did I want to say here? So at the point where it encounters the glass, the crests have to remain the same distance apart. So these crests are obviously all the same distance apart. That distance has to be maintained here as it enters the second medium. So the only way for that to happen is for the light to reflect. Now once it's all in the glass, the speed changes, so then the wavelength and frequency can also change in accordance with that. Okay, so is there a way to determine how the light will bend? And the best example I've seen is to think of a car. Okay, so up here, let's say we have a smooth road, and down here we have a bunch of muddy road, or maybe muddy off-road, okay? And we have our Jeep just traveling along on this smooth road. It's going off-road, and as soon as this front tire here hits the mud, what's gonna happen? Well, this front tire suddenly can't spin as fast as it was on the smooth road. So this front tire is gonna slow down, while the other 3 tires are still going the same speed as they were on the smooth road. So instantly what's going to happen is he's going to turn. Okay, so he's coming in, this first tire hits the mud and slows down, the other tires are still going the same speed, so the Jeep's going to turn. Hopefully you can see that okay on the video, what's happening without my hand in the way. This first tire encounters the mud. It suddenly is moving slower than the other 3, so the other 3 are going to pull it down a little bit, change the angle. Okay. I'm going to ask you to watch a Khan Academy video, and he will also try to explain this truck thing, and hopefully by the time it's all over between the 2 of us, it'll make sense. Okay, we can also calculate using math how it will bend using something called Snell's law. Okay, Snell's law was named after Willebrord Snell, and he discovered this in 1620, but what he figured out was this mathematical equation, n1 sine 1 equals n2 sine theta 2. Okay, now what does all this mean? Okay, n1 and n2 are both indexes of refraction. Okay, and we abbreviate that with an n. So but n1 represents an index of refraction, n2 represents a different index of refraction. So what is an index of refraction? It's the ratio of the speed of light in a vacuum over the speed of light in some other medium, like glass, water, pudding, I don't know. Okay, so another way to say this is that N equals C over V, the speed of light in a vacuum over the speed of light in something else. Now we're going to make an assumption here that the speed of light in a vacuum for all intents and purposes equals the speed of light in air. Okay, these two values are so close, we're going to consider them equal. All right, and we're going to say that N of air then is 1.00. Okay, because it would be the speed of light in a vacuum over the speed of light in air. If we assume these two things are equal, then N obviously is going to equal 1. One thing over itself is equal to 1. And then if you think about it, all other substances that light could pass through are going to be denser than air. So all other N's, all other of these index of refractions should be greater than 1. Okay, because we're going to have the speed of light in a vacuum and then the speed of light in anything else. Well, no matter what this other thing is, it's going to be smaller. This speed will be smaller than this speed, which will make N greater because we're dividing by a smaller number, which will make N greater than 1. So if you're doing any of these problems and you get an index of refraction that's less than 1, you've probably done something wrong. Okay, so the index of refraction for air is 1.00. All other index of refractions should be greater than 1. Okay, so maybe if we draw some pictures, this will become more clear. So let's say we have air, and then down here we have glass. Okay, and we have some light coming in. Okay, so here's our light source. All right, how do we expect this light to bend? Well, glass is more dense than air. So if we think of our Jeep example, when this tire hits the glass, it's going to slow down. It's going to make the Jeep turn a little bit. So we expect it to bend down a little bit, as such, to be refracted like that. Okay. So when we're talking about these angles, theta 1 and theta 2, I'm going to try to show you where those angles are. This is theta 1. This is theta 2. Again, it's the angle that would be created if we made an invisible perpendicular line to the line that results from where the two different mediums intersect. Okay, so above the line we have air, below the line we have glass. I'm going to draw an invisible perpendicular. This is my theta 1. This is my theta 2. Okay, this is also called the angle of incidence. Okay, that's nothing new. We used this term before when we were talking about the law of reflection. This angle is the angle of refraction. Okay, so now we have 3 different angles that we've talked about. The angle of incidence is always the angle that the incoming light makes with the perpendicular. We've also talked about the angle of reflection. Okay, and the angle of reflection of reflection. So theta 1 is always equal to theta 3. Now we're introducing this angle of refraction, which is the angle again made in reference to that imaginary perpendicular line here. Okay? So in Snell's law, we have sine of theta 1, sine of theta 2. Theta 1 and theta 2 are measured in reference to this imaginary perpendicular line. Okay, they're determined relative to that perpendicular line. Now, one common mistake that I've seen over the years that students make is they get mixed up with n1 theta 1, n2 theta 2. So just for a rule of thumb, I would keep all my 1s above the line, all my 2s below the line. So this is n1 theta 1, this is n2 theta 2 down here. Okay? So maybe this will become more clear if we look at a concrete example. So let's look at example 12.4 on page 402. Okay, get to my example, page 402. Okay, so it says a light beam is shining on a pane of glass. Okay, so it's coming through the medium of air. Okay, and it's encountering glass. So we expect it to bend a little bit like this. Let's go ahead and draw our imaginary perpendicular. Right, so this is our theta 1. This is our theta 2. Because remember, we're going to keep our n1 theta 1 up here, n2 theta 2 down here. In air, we know that the index of refraction is 1.00. In glass, it tells us that the index of refraction is 1.5. Okay? The problem also tells us the angle of incidence is 34.5 degrees. Now remember, this is the angle of incidence. So we know that's 34.5 degrees. So Snell's law says that n1 sine theta 1 equals n2 sine theta 2. I'm sorry, and the problem is asking what is the angle of refraction. So we're trying to solve for theta 2. All right, so let's look at how we solve for theta 2. The first thing we would do is divide both sides by n2. Okay, so then I would have n1 sine theta 1 over n2. These two things would cancel out, and I would have sine theta 2. So then I would take the inverse sine of all this, and that is theta 2. Okay, so I would have the inverse sine, n1 is 1.00, times sine of theta 1 is 34.5 degrees, all over n2, which is 1.5. The inverse sine of that equals theta 2. And if you do all that math out, theta 2 is equal to 22 degrees. Okay, so we've just determined that this angle here then is 22 degrees. Now let's sit back and just think about it. Does that make sense? Does it make sense that the angle of refraction would be less than the angle of incidence? Yes. So I can be confident that I'm on the right track. because I got a reasonable answer. Okay. So at this point, you can stop the video and you can watch the Khan Academy video that I'm suggesting that you watch, or you can keep going and watch the Khan Academy video at another time. But I would encourage you to watch the Khan Academy video. It'll just reinforce these concepts further. Okay, the last part of the chapter then that we're going to talk about is lenses. Okay, and lenses are a pretty powerful thing. I wear glasses every day with lenses in them. So we're going to see how lenses work. Again, lenses are made of glass or something similar to glass. So they're a transparent material that will refract light as it's coming in. And that's what helps us see well. Maybe you guys can hear my dog walking around. So there's two types of lenses we're going to study. Okay, Chance. Hey, buddy. Okay, you gotta leave me be, because I'm taping. Okay, we're gonna talk about, hey, Greg, can you come get the dog? We're gonna talk about converging lenses and diverging lenses. And those are the two different kinds of lenses that we're gonna talk about. So a converging lens looks like this. A diverging lens looks like this. So let's focus on converging lenses first. Okay, so to draw a converging lens, again, it looks like this shape. And it's called converging. Well, let me give you a little bit more information. There's no radius with a converging lens because it's not part of a circle, but there are focal points, and because light can pass either way through the lens, there's a focal point on each side. Okay? So with a converging lens, as light passes through horizontally, all horizontal light converges onto the focal point on the opposite side. Okay, so no matter where these horizontal light beams come through the converging lens, as long as they're horizontal, they're going to converge on the focal point on the opposite side. And that's why it's called a converging lens. Okay, this is also shown on figure 12.9 on page 406. So we're going to draw these converging lenses kind of fat, just so we can see what they're doing and how the light's bending. But in reality, the lenses are very thin. We already talked about there's a focal point on each side because light can travel through coming from either direction, and that there's no radius. There is, however, another point that we're going to use. In all of our examples so far with our lenses and mirrors, we've had this horizontal reference line. On lenses, we're also going to draw a vertical reference line, and we're going to be using the center point here in our ray tracings. Okay? So for lenses, we're going to do ray tracings just like we did with mirrors. And there's a process for lenses, just like there was with mirrors. So let me jot down what that process is, and then we'll go through some examples to show you how this works. Okay, so the first thing we're going to do is draw the lens. And the second thing we're going to do is draw our horizontal and vertical reference lines. Third, then, we need to find both focal points. One on each side. One on the right, or one on the left, one on the right. Okay, just like with mirrors then, we're going to draw our person And then just like with mirrors, we are going to draw 3 lines that will help us predict how the image will look as it passes through the lens. Okay, the first line we're going to draw is a horizontal line, and it will exit through the focal point. The second line we're going to draw is it will enter through the focal point and exit horizontally. Okay, so just like with our mirrors, with lenses, these first 2 lines are kind of opposite each other. The first one, it's going horizontal, it's exiting through the focal. The second one, it's going through the focal, exiting horizontally. The third line, just like with mirrors, I think is the easiest. It's going to enter through the center and not bend at all, and exit through the center. Okay, so we'll draw our 3 lines to help predict how our image will look. Then we'll find the intersection point of the 3 lines. And where they intersect, we're going to draw our head. And then from the head, we're going to draw our body back to the horizontal. Okay, so a very similar process to what we used when we were looking at mirrors. A few slight changes, but very similar. Okay, so let's look at an example. Maybe I can fold this down so we can still see our process here. So let's look at an example from the book. So example 12.5. Okay, so this is on page, let's see, page 406. Okay, so it says we have an object or a person standing 10 centimeters from a converging lens that has 7 centimeter focal points. What is the appearance of the object? Okay, so let's start with number 1. We're going to draw our lens. Okay, number 2, draw our horizontal and vertical reference lines. So this should just divide the lens through the middle. Find the focal points. Well, in this example, it said it has 7 centimeter focal points. So maybe I'll just actually measure these. And then the object is 10. Well, our man is way out here. Okay. Okay, so we have found both focal points. We've drawn the person. Now let's draw our 3 lines. Okay, so the first one, the man's looking horizontally through the lens. When he gets to the center point of the lens, the center vertical line, the light is going to refract or bend toward the focal point. Okay, it's different from mirrors because light's actually passing through. It's not being reflected back because this isn't a reflective surface. This is a transparent medium. So he's going to look through. When it reaches the center point, it's going to bend toward the focal point. Okay, second line, green line. It's going to enter through the focal point. I drew my man too tall. So we have to pretend our lens comes all the way down here. And it's going to exit horizontally. All right. And then finally, our third line, our purple line, it's going to enter through the center and exit through the center and just keep going. Okay, and now I've drawn my picture way too big, but you can see these lines eventually would intersect. They're all moving toward an intersection down here. I mean, it would be way off my paper, but we can get the idea of what it would look like. So in this case, the image would be inverted or upside down. It's obviously magnified. And it's real because I didn't have to do any extrapolation. These light rays are all eventually going to intersect down here. Okay, so sorry, this drawing wasn't, I made it way too big. But anyway, hopefully you can see how it would look, and you can always look at the example in the book too. Okay, lastly, we're going to talk about diverging lenses. Okay, and diverging lenses look like this, kind of hourglass shape. Okay, and they're called diverging. Let me draw my horizontal and vertical. They're called diverging because as horizontal lines come in, they refract away from each other. Okay, so they don't converge over here, they diverge and spread out. So this is shown in figure 1210 on page 408. Okay. We use the same process as we've used before, and we'll use that process again. One thing to note on the process is when you're drawing your horizontal and exiting through the focal point, you want to use the focal point on the same side. Remember, there's two focal points, so you want to use the focal point on the same side as the object. When it's traveling toward F, hold on here. Yeah, when it's traveling toward F on the opposite side, then that's how you want to draw your horizontal. So on this, you use the focal point on the same side as the object. On the green line, you use the focal point on the opposite side of the object. Okay, that's the only tricky part, I think, with these diverging lenses. Focal point on the same side, focal point on the opposite side. Because there's two focal points, we have to keep them straight. Okay, so again, let's look at an example. Example 12.6, and this is on page 408. So it says an object is 7 centimeters away from a lens that has a 5 centimeter focal point. It doesn't exactly say what kind of lens, but we're talking about diverging lenses. So we're going to follow our process. So number one is draw our lens. Now we're going to draw our vertical and horizontal guidelines. Here's our center point. Step 3 is define both focal points. The problem says we have focal points at 5 centimeters. So here's one, and we'll say here's the other. These are both at 5. And then our person is 7 centimeters. So he's standing about right here. Okay. Now we're gonna go into drawing our 3 lines. So we're gonna draw our horizontal. When it meets the vertical line is when we're gonna bend, and remember this is a diverging, so we're gonna use the focal point on the same side, and this light ray would be refracted up like this. Okay, our green line then, it's going to go toward the focal point on the opposite side. Okay, so not this one on the same side, but toward the focal point on the opposite side, and then exit horizontally. So it's going toward the focal point on the opposite side. When it hits the center line, it's going to be refracted horizontally. And then finally our purple line, which is the easiest, it's going to go through the center and just keep going straight through the center. Okay, so obviously these 3 lines are not going to intersect, so we have to extrapolate. So this one would be, green line would be extrapolated as such, orange line would be extrapolated as such. They're going to intersect here. At the point of intersection, I draw my head, I draw my body back down to the horizontal, and this object then is going to appear reduced, upright, and it is a virtual image because I had to extrapolate the lines. So the same 3 characteristics that we use when we were talking about mirrors. Is it reduced or magnified? Is it upright or inverted? And is it a real or a virtual image? Okay, same 3 criteria. Okay, so just remember on these, horizontal lines are going to diverge. They're going to move away. That means you use the focal point on the same side. The green line, it's going toward the focal point on the opposite side as the person, and then refracting horizontally. Okay, the only other section left in Module 12 then is about the human eye, how God created the eye, how our eye can focus, and how it focuses differently than a camera. So I'd like you to obviously read through that. There'll be some review questions, and I think there's a test question about that, so read through that. If you have any questions over the material, please post them to Google Classroom so that everybody can see the question, and I will post my answers out there so everybody can see the answer. And just if you have any concerns about how this is going, let me know. This is uncharted territory for all of us, so we'll just try to find a solution that works, but hopefully these YouTube videos have been helpful. So hope y'all have a great week, and we'll touch base soon.